1.3, complex numbers. So starting with the complex numbers, the first thing we're going to talk about is imaginary numbers. No, these aren't ones that we made up. Imaginary numbers are numbers that, and I hate to say this, aren't real. So when we're talking about complex numbers, we're talking about either real numbers or imaginary numbers. Well, what's an imaginary number? Well, when we look at a radical, if we have a positive value under the radical, then we get a real number. That number may be rational if it's a perfect square, or it may be irrational if it's not a perfect square. But if we put a negative number underneath that, said if a is great, making sure that a is greater than 0, therefore negative a is going to be a negative number, you should remember that you can't take the square root of a negative number. If you plug that into a basic calculator, it's going to give you an error. I say a basic calculator because if you have a graphing calculator or a better scientific calculator, it can actually give you a result for that. And why can it do that? Because anytime you take the radical of a negative number, the result is what we call an imaginary number. So this radical of negative a is the same as saying I radical a, where I is the imaginary number. So it's the imaginary number I. Well, what is I? I is equal to the square root of negative 1. And that's how we define it. So I squared, if I square both sides, is equal to negative 1. So that's how we define the imaginary number. If I take this negative a, I can break up that radical into two pieces. Remember, when you have radical a times b, you can break that up into radical a times radical b. So if I have radical negative a, I can break that up into radical negative 1 times radical a. We define I as being the radical of negative 1, so you have I radical a. And that's what we're talking about when we deal with imaginary numbers. Now that we have this definition, the imaginary number I is equal to the square root of negative 1, now I can take the square root of negative numbers. The square root of negative 4 is equal to the square root of negative 1 times the square root of 4. Square root of negative 1 we said was I. Square root of 4 is 2. Don't need that radical sign there. Times 2, so we write that as 2i. Now when we write imaginary numbers, we put the constant in front of the I. So it's kind of like we deal with variables, right? You don't put a5, you put 5a. Don't put x3, you put 3x. So you don't put I2, you put 2i. If I take the square root of negative 5, we know that I can split that out into the square root of negative 1 times the square root of 5. So I can just say, if there's this negative here, I can bring that out as I, and that leaves me with the square root of 5. Now when we have an imaginary number multiplied by the radical of a number, we do put the I in front of the radical. So the correct way to write this is I radical 5, whereas here we put it after 2i. And the main reason for this switch is because if we were to put it after you can see that it could very easily get mistaken as the square root of 5i. So if for no other reason, it's just to make it so that it's less confusing and less likely to have a mistake be made. So if you're dealing with a radical, you pull out the imaginary and you still have a radical, put the imaginary first, I square root of 5. If the radical is able to be taken and we come out with an actual value for it, then put the I afterwards. So that's dealing with imaginary numbers, and you can do that with any negative radical. Pull out the I, take the square root of whatever's left over. So where do these complex numbers come in? Well, complex numbers are numbers that can be written in the form a plus bi. A being the real part, bi being the imaginary part. So you have a real part and an imaginary part. If we think of our grouping of how you could sort these different sets out and everything, we now have complex numbers within complex numbers. You can have real numbers. So complex numbers are in the form a plus bi, where a and b are not equal to 0. Real numbers are in form a, right? Real numbers do not have the imaginary part. And then we have imaginary numbers, which can be written in the form a plus bi. Right, so complex numbers is this overarching thing. It includes strictly real or the imaginary numbers, complex numbers that include imaginary and possibly a real part. But then actually inside of this, if I extend out this circle, you can also have pure imaginary. Which is just bi. So we can end up with having complex numbers that are purely real. They don't have an imaginary part. Complex numbers that are imaginary, and they include a real part and an imaginary part, and complex numbers that are pure imaginary, meaning that they have an imaginary part but they do not have a real part. So it kind of breaks up into these different pieces. So imaginary numbers can have a real part and an imaginary part. So you kind of lump on this real number side all this other stuff that we've dealt with previously, all the different number sets, the natural numbers and the integers and the rational numbers and the irrational numbers, etc., etc. Okay? So now that we have these, we can start looking at them a bit. Okay, I just want to make sure I'm everything, so we covered that. So let's get on to operations with complex numbers. So we're going to start with products and quotients of complex numbers. So we have one complex number, a plus bi. We have another complex number, c plus di. And if we take the product, so a plus bi times c plus di. Now you should look at this and go, gee, well, isn't that just a binomial times a binomial? And the answer is yes. You have a binomial with a real part, with a real term and an imaginary term, purely imaginary term. You have another binomial with a real term and a purely imaginary term. So when we multiply these, we can just FOIL. First, AC, outer, plus ADI, inner, plus BCI, last, plus BDI squared. Now remember we said that I is equal to the square root of -1, and that I squared is equal to -1. So we see that this I squared, we can replace -1. We can also combine these two terms because we have an imaginary and imaginary. So I can say AC plus AD plus BC I minus BD. Where'd that minus come from? I squared is equal to -1. So I have plus -1 times BD or minus BD. So the last part is just to combine the real parts together, and we end up with AC minus BD plus AD plus BC I. And you look at that and go, wow, what exactly did that do for me? Am I better off just doing the multiplication? Well, in reality, you are. Unless you happen to enjoy memorizing random formulas, like AC minus BD plus AD plus BC. If you have a memory like mine, that's memorizing this is just not going to work. For some of you, you may be able to memorize that, and if that's the case, go ahead and do it. Otherwise, just remember, all you're doing is FOILing. The big thing to take account of is this, that you're going to end up with I squared, and I squared is not just like x squared, where you have to leave it there as a variable. I squared is -1. So you're going to, anytime you get an I squared, you're going to turn that into a -1, which means you're going to subtract that piece. So let's give it a shot. Five plus 2i times 3 minus 4i. So we're just going to FOIL it. 5 times 3 is 15. 5 times -4 is minus 20i. 2i times 3 plus 6i. 2i times -4i, -8i squared. So now remember, this I squared is going to turn into -1, so if you want, you can just kind of do this, right? If you have minus 8 times -1, then that's the same as plus 8. So now I can combine like terms. 15 plus 8 is 23, then minus 20i plus 6i, so minus 20 plus 6, minus 14i. And we just multiplied two complex numbers. So see the process, same process. First, outer, inner, last. But just remember, this isn't a variable, this is the imaginary number I, and I squared is equal to -1. So we turned it into plus 8 instead of minus 8, giving us 15 plus 8 is 23, minus 20i plus 6i is minus 14i. So that's multiplying complex numbers. Not that bad. If you can multiply binomials, you can multiply complex numbers. Just remember I squared is equal to -1. Common mistake that I see people make is they leave that I squared in there instead of turning it into -1. Because once you turn it into -1, you can combine the real parts. Okay, well, what about quotient? So if I have A plus BI divided by C plus DI, well, what can I do with that? Well, I'm dividing a binomial by a binomial. Now, when I look at this, I see this I here that makes things difficult. I obviously can't factor anything out. I've got A, B, C, and D. Can't factor anything out. This is a binomial, not a monomial, so I can't even break it up into A over C plus BI over C. and stuff like that. That's not going to work. But I see this oddball I in here, and I start thinking of rationalizing denominators. And the reason I start thinking of that is, remember when you had a radical in the denominator, or call it a complex radical, a plus the square root of b. Then what we did to get rid of that radical was we multiplied by its conjugate. Well, what we're going to do here to get rid of this imaginary part is we're going to multiply by the complex conjugate. C plus di, its complex conjugate, is going to be C minus di. Remember, complex conjugate just means you change a plus to a minus or a minus to a plus. So now that I have that, well, why would I do that? Here's why I would do that. Because if I take the complex conjugate, I'm now multiplying, I'm doing the product of a sum and a difference. And we know that the product of a sum and a difference is equal to the square of the first term minus the square of the second term. If I square this di term, I'm going to end up squaring that I. The square of I is -1, which means we're going to get rid of the imaginary part in our denominator. So I've got to, obviously, if I'm multiplying the bottom by the complex conjugate, I've got to do the same thing on the top. So C minus di. And now that I do that, I'm really, on the top, I've got just the standard multiplying two complex numbers, which we just did. On the bottom, this is the product of the sum and the difference, which means, let me do the bottom one here first. That means the square of the first term, c squared, minus the square of the second term, di squared. So I'm going to just write that as di squared, just to show the step that we're doing. Remember, on the top, we're going to multiply through, so a times c. I should do that just to clarify, it shouldn't be necessary, but just to make me feel a little better. So a times c, a times, so minus a d I, bci, minus bdi squared. So we got that there. Continuing on. Well, remember with this, I squared is -1. So I'm going to do the same thing again. -1, I'm just going to make that plus. So now I've got AC plus BD is the real part, and then minus AD plus BCI, so minus AD. Now be careful with this because it's very easy to make a mistake here. If I put a minus out here and do AD plus BCI, then I won't have distributed a negative through. So if I'm going to put this out here, I would have to make this minus BCI. So what I'm going to do instead, to make my life a little easier, I see I've got plus BC minus AD. I'm going to go plus BC minus AD I. It just makes it a little bit simpler. But see what was going to happen if I just take this part here and I try to pull out this negative AD and this plus BC, I would have to say plus, and then in parentheses, negative AC plus AD plus BC. If I pull the negative out, then yes, I make that positive, but it makes that negative. So rather than dealing with that, I just said, well, okay, this one's plus, that one's minus. Just put the positive one first. So I've got that in my numerator. And then in my denominator, remember that di squared, one of our power rules says that this squared, gets distributed through the two of them, turning that into d squared I squared. Well, I squared is what? Negative 1. Right? So now we have c squared minus d squared times negative 1, or minus negative d squared, or plus d squared. So we end up with c squared plus d squared. Now, if you remember the product and sums and differences, if you have x plus y times x minus y, that's equal to, should draw an x, not an a, right? That's equal to x squared minus y squared. X times x gives you x squared. X times negative y gives you negative xy. X times y gives you positive xy. Therefore, xy and negative xy cancel out, and then y times negative y gives you negative y squared. But when you're dealing with complex conjugates, the product with sum and difference with complex conjugates, we end up with that last term. Yes, it's squared, it's the difference of the squares, but that last term has an I squared in it, which is negative 1, so it makes it plus. So the product of sums and differences, when you're dealing with two complex numbers, becomes, you could say x squared plus y squared, or in this case c squared plus d squared, becomes the sum of squares as opposed to the difference of squares. And as you do this more times and you make sure that you cancel out your I squareds becoming negative 1 and changing signs, you'll get used to this and you'll feel that that's the way it should be. Initially it can throw you off because you go, oh, well, this is the product of the sum and difference, and you want to put that negative in there, but the I squared is going to change it to a positive. So it's going to change it to addition. But that's the way we do that. So let's do this with a real number. And yes, you could memorize this formula again, but I almost have to say, are you feeling okay if you want to memorize this formula? You're better off, in my opinion, and it's strictly my opinion. There is no right and wrong with this. You want to memorize the formula, it's perfectly fine. But personally, I'd rather just go through the math than memorize that formula. You just think of that formula and think how easy it is to get a sign in the wrong spot, or mix up, scramble one of the letters with another one, and so things come out wrong. So what if I have 3 plus 2i divided by 4 plus 5i? So what are we going to do? We're going to multiply by the complex conjugate of the number in the denominator, so 4 minus 5i. 4 minus 5i. Remember, you always multiply the top and bottom by the same thing. Well, what's that going to do? Well, 3 times 4 is 12. 3 times negative 5i, negative 15i. 2i times 4, 8i. 2i times negative 5i, negative 10i squared. For the denominator, that's the product of the sum and the difference, they're complex conjugates, so it's going to be the difference of squares, but it's going to be the sum of squares. So 4 squared is 16, plus 5 squared is 25. Because it would give us 25i squared, so we'd have 16 minus 25i squared, but I squared is negative 1, so it gives us 16 plus 25. If it makes you feel better, I'll do that right now just to show one more time. 16 minus 25i squared, 5i times negative 5i, right? And then remember that I squared turns into negative 1, so giving us the positive there again. So 12 plus 10 is 22. Minus 15i plus 8i gives us minus 7i. Over I squared is negative 1. So 16 plus 25 is 41. Now we can stop right there, but really what we like to do is we like to get back to a complex number. And right now we have a complex number being divided by a real number. So this is where we can take one more step and say, okay, that's 22 plus 7i over 41, or that's 22 over 41 minus 7 over 41i. So that's written in the form a plus bi, where a is 22 41st and b is negative 7 41st. And of course, if we can simplify either one of these, we do, but we can't. Factors of this are 2 and 11, neither one goes into there. Factor of this is 7, that's not divisible by 7, so we can't simplify anymore. But that's written in the form a plus bi. This would not be considered complete. I would have to take off a point on this because you did not put it in the form a plus bi. Fractions are okay. Remember, we've reached the point in mathematics where fractions aren't considered to be taboo. They're not scary. Okay? We can leave something as a fraction and not have to stress about it. Unless it says specifically to turn it into a decimal or whatever. But we should realize also that leaving it as a fraction is actually the more exact answer. If I take 22 and divide it by 41, I'm going to get an irrational number. Well, I'm going to get a rational number because obviously an integer divided by an integer, but we're going to have to go out a number of decimal places to do that. I'm guessing, well, actually I don't know what that, but a number of decimal places, and eventually we will either terminate or get a number of repeating digits. So it's better to just leave it like this. So I would suggest doing that. Okay, so that's multiplication and division of complex numbers. Well, let's look at addition and subtraction of complex numbers. And I'm going to put these both together at the same time instead of doing it separately because remember, addition and subtraction are really the same thing. So addition, subtraction, complex numbers. So if I have a plus bi plus c plus di, we're going to treat this just like we did when we were adding polynomials. We're going to combine like terms. So that's going to give us a plus c plus b plus d I. So it's really no different than when we had a variable in there. That I can be treated as a variable. We're going to add the real parts together. We're going to add the imaginary parts together. And that's it. If we have subtraction, I'm going to switch over to black and see if it works well enough for us to do this. If I have a plus bi minus c plus di, well, I'm going to distribute that negative through, so I'm going to have a minus c plus b minus d I. Because I just distribute that through, I get minus c minus di, and I combine like terms again. So that's the only real difference, so that's why I say, well, let's just look at this all together. So let's run one and see what happens. In reality, addition and subtraction are much easier than multiplication and division. Multiplication and division, you have to play with all these things. Well, what happens when my I square is squared? What happens if I've got an imaginary number in the denominator, etc., etc. But when we're adding or subtracting, not really a problem. So if I have 7 minus 3i plus 2 plus 5i, just like with polynomials when we were adding them, when you're doing addition, those parentheses really mean nothing. It's just combining like terms. So those parentheses can be removed. And it's the same thing, right? So 7 plus 2 is 9, minus 3i plus 5i plus 2i, and we're done. Simple enough. Well, what if we're subtracting? Magic of the whiteboard, we've got a different problem. So 7 minus 3i minus 2 minus 5i. Well, how do we subtract? We change it to addition, right? Keep change. So that's 7 minus 3i minus 2 minus 5i. And we combine like terms. 7 minus 2 is 5. Minus 3i minus 5i minus 8i. And we've just subtracted complex numbers. So not hard to deal with. If you can deal with adding and subtracting polynomials, and this is really just adding and subtracting binomials, then you can add and subtract complex numbers. If you can multiply binomials and do FOIL, and remember that I squared is equal to -1, then you can multiply complex numbers. If you can rationalize a denominator that has a complex denominator where it has a real, we'll say, a real part and a radical part, if you can do that, then you can divide complex numbers because you use the same process. So that works very well for us. This is a subtraction, multiplication, division, not bad. Okay, so continuing on from there, I already talked about properties of complex conjugates, but I just want to make sure I write it down so you've got it specifically. A plus bi times a minus bi is equal to a squared plus b squared. So that's multiplication of complex conjugates. Remember, the only difference from the product of a sum and a difference is because it's complex and you've got I and I, you have a squared plus b squared, whereas we're used to seeing a squared minus b squared. Okay? So last thing I want to cover is simplifying powers of I. Well, if we think about what I is, so if we have I is equal to I to the 1, isn't it, right? Anything to the 1 power is itself, which we said that was equal to the square root of -1. And we said that I squared was equal to -1. I cubed is equal to I times I squared, right? I to the 1 times I to the 2 gives you I to the 3. You add up the powers. So that's equal to -1 times the square root of -1, or negative square root of -1. Or I should say, even rather than that, I squared is -1. I is the square root of -1, right? So we have I, so we can just say that's negative I. I'm going to put this here and just remind us that I to the 1 is equal to the square root of -1 is equal to I. So I'm just going to leave those on that side so we see what's happening. And then I to the 4th, well, isn't that I squared times I squared? I squared times I squared. Well, I squared is -1 times I squared is -1. -1 times -1 is 1. What about I to the 5th? Well, I to the 5th is I to the 1 times I to the 4th. I to the 4th is 1. Okay. Well, 1 times anything gives you that thing, so I to the 5th is I again. I to the 6th, I to the 4th is 1, so I squared times I to the 4th gives you I to the 6th. So I squared times I to the 4th. I to the 4th is 1. So every time we have that, it's just gonna start cycling through, or we can, that's I squared or -1. So what's gonna happen is we have I is equal to I. I squared is equal to -1. I cubed is equal to -I. I to the 4th is equal to +1. I to the 5th is equal to I. I to the 6th is equal to -1. I to the 7th is equal to -I. I to the 8th is equal to 1. I to the 9th is equal to I, etc., etc., etc. Right? Get my dots going down here. So you can see that we have a pattern. I, -1, -I, 1. I, -1, -I, 1. I, etc., etc., etc. So basically, since we can break these up into I to the 4th times something, anytime you have a power greater than 4, start pulling out groupings of I to the 4th. Every time you do, you're pulling out a 1. Okay, you factor out a 1, you're left with what's over, but it doesn't change the value. So let's look at what that does for us. If I have I to the 17, well, I to the 17th is I to the 4 times 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 I to the 1. I to the 4 is equal to 1, so that's 1 times 1 times 1 times 1 times I to the 1 is I. 1 times 1 times 1 times 1 is 1, times I is I. So I to the 17 is equal to I. So that's pretty cool. So that means no matter what I've got, what I can do is I can, sometimes referred to as modulus, but I can divide by 4 and then just use the remainder to determine what I'm going to be at. So if I took 17 and I divide it by 4, I get 4 remainder 1. Right? 17 divided by 4 is 4. 4 goes into 17 4 times with a remainder of 1. It became I to the 1, which is I. So the remainder tells me the power. The power is going to be 1, 2, 3, or 4, so it's either going to be I, -1, -I, or 1. So let's do another one. I to the 22. I to the 22, well, if I divide that by 4, then I get 5 remainder 2. So that's equal to I squared, which is equal to -1. Now, isn't that cool? So that's pretty, and that makes it pretty simple. We just divide by, keep pulling out 4s, and the remainder is going to give us our value. But what if this is a negative? What if I have I to the -15? Well, what's that going to do to us? Well, if you have a negative exponent, that says this is 1 over I to the 15. What do you do if you have an imaginary number in your denominator? The equivalent of rationalizing, right? We want to get that imaginary number out. Well, how do we do it? Well, there's 2 options we can do here. What I look at it as is, well, I've got 15 here. What do I need to turn this into 1? Right? To turn it into 1, I need this to be divisible by 4. So if I multiply top and bottom by I to the 1, then I'm going to end up with I to the 16, which is divisible by 4 with a remainder of 0, which means I have 1 in the denominator. Oops. You should always put the equal sign, then put your fraction, not put it under the equal sign. Right? So we have that's 1, and 1 times I is I, so that's going to be I. So to me, that's the quick, easy way to do it. Okay, put it in the denominator. What do I need to make it so that this turns into 1? I just need this to be a value that's divisible by 4. And then once I've got that, I multiply the top and bottom by that value. Remember, if you multiply a fraction by the same number on the top and bottom, you get the same fraction, or an equivalent fraction, right? So that just allows us to cancel that out, and we end up with whatever is left over. So I hope you enjoyed dealing with complex numbers.